Hello friends. So, welcome to lecture series on multivariable calculus. So, in the last lecture I have discussed about Taylor's theorem, that how can we write Taylor's theorem for two or more than two variable functions. So, how can you write that? That if you have say f of x naught plus h, y naught plus k, so that will be equals to f of x naught y naught plus h del by del x plus k del by del y of f at p naught plus 1 by factorial 2 h del by del x plus k del by del y whole square f at p naught, and so on 1 by factorial n h del by del x plus k del by del y whole raised to power n f at p naught plus remainder term. Okay, where p naught is x naught y naught. Now, if we want to find out linear approximation of this f at x naught y naught, so how can we do that? We simply put x equals to x minus, we simply replace x is equals to x naught plus h and y is equals to y naught plus k. When you replace x by x naught plus k and y by y naught plus k and takes the term up to power 1, okay, then we get the linear approximation of this f. So, what is a linear approximation? Lxy of fxy at x naught y naught is simply f x naught y naught plus this h will be x minus x naught f x at p naught plus y minus y naught f y at p naught. So, this will be the linear approximation of this f at x naught y naught. And what is the quadratic approximation? Quadratic approximation qxy of fxy at x naught y naught will be simply qxy is equals to f x naught y naught plus, now you will take term up to here, you first expand this and then replace h by x minus x naught and k by y minus y naught. So, what we will obtain? This is simply x minus x naught f x at p naught plus y minus y naught f y at p naught plus this will be 1 by factorial 2. So, this term is x minus x naught whole square f x x at p naught plus this is 2 x y x minus x naught y minus y naught f x y at p naught plus y minus y naught whole square f y y at p naught. Okay. So, this is the quadratic approximation of this f at x naught y naught. Now, if you find linear approximation or quadratic approximation, how accurate our approximation is, or how can we find out the bound of the error? Okay. So, this lecture is deal with error approximation. So, let us go with this lecture now. Now, suppose you find linear approximation Lxy of fxy. Now, to find the error in the linear approximation, first let us suppose that first and second order partial derivative of f are continuous throughout an open set containing a closed rectangular region R centered at x naught y naught and given by mod x minus x naught less than equals to h and mod y minus y naught less than equals to k. So, let us discuss this. So, if we write linear approximation of f at x naught y naught, So, that will be f x y is equals to f x naught y naught plus x minus x naught f x at p naught plus y minus y naught f y at p naught, and plus we write remainder term. Okay. So, this is L x y, which is the linear approximation of this f at x naught y naught, and this is a remainder term or the error term. How you find Rn x now? Rn. Now, Rn will be given by, here we are taking we are finding linear approximation, I mean n is equals to 1. So, we will put n equal to 1 here. So, this will be this is h del by del x plus k del by del y whole raised to power n plus 1, that is 2 upon factorial 2 f second derivative at x naught plus theta h and y naught plus theta k, where theta is between 0 to 1. Okay. Now, when you replace h by, you simply expand this and replace h by x minus x naught and y by and k by y minus y naught. So, what you will obtain? So, this will be oh sorry, this derivative will not be here because this is included here. Okay. Now, this will be, when you open this, it is 1 by factorial 2, h is x minus x naught, it is f at, say it is p dash plus 2 x minus x naught y minus y naught f at p dash plus y minus y naught whole square f at p dash. Oh, it is f x x, it is f x y, it is f y y. Okay. Now, you simply expand this, okay, take the power 2, simply expand this and replace h by x minus x naught and y by and k by y minus y naught. So, you will get this expression at p dash, where p dash is simply, where p dash is this point x naught plus theta into x minus x naught and y naught plus theta into y minus y naught, where theta is between 0 and 1. Now, how we can find the bound of this error? So, this will be given by the error term for linear approximation. How can you find out an upper bound of this error? So that we can say that the approximation, that the error concerned with this approximation is, the maximum amount of error will be this much. How can you find that? So, to find this, so this is our R1. So, mod of R1 will be equal to 1 by 2 mod of, so it will be less than equals to, you can say, mod of x minus x naught whole square f x x at p dash plus mod of x minus x naught mod of y minus y naught f y y f x y at p dash plus mod y minus y naught whole square f y y at p dash. Okay, by this expression where p dash is this point. Now, let us suppose in this region R, which is x minus x naught less than equals to h and mod y minus y naught less than equals to k, in this rectangular region, the maximum value of mod f x x, mod f x y and mod y y is R, is m. The maximum value of mod f x x, mod f x y and mod y y over this region R, suppose this is m. Okay. So, we can say that this is less than equals to, this is less than equals to m, this is less than equals to m and this is less than equals to m, and m we can take out. So, this will be m by factorial 2, this will be mod x minus x naught whole square plus 2, so 2 is here. So, it is 2 mod x minus x naught mod y minus y naught plus mod y minus y naught whole square. So, this is equals to m by factorial 2 and this is mod x minus x naught plus mod y minus y naught whole square. So, this is an upper bound of the error term. So, basically this will give an error term concerned with the linear approximation of f x y. So, let us solve some problems based on this. Find the linearization L x y of the following function at p naught and also find the maximum error in the specified region R. Suppose we have the first problem. The first problem is f x y is equal to, this is x square minus 3 x y plus 5 and p naught is 1 comma, it is 2 1, sorry, it is 2 comma 1. So, first we have to find out the linear approximation of this f. So, linear approximation is given by f at 2 1 plus x minus x naught, this is x naught and this is y naught. So, x minus x naught f x at p naught plus y minus y naught f y at p naught. So, what is f x at p naught for this f? F x is given by 2x minus 3y and f x at p naught will be 4 minus 3, that is 1. Now, what is f y? Del f by del y, this will be minus 3x and f y at p naught will be, from here it is minus 6. So, this will be equal to, when you substitute x equal to 2 and y equal to 1. So, it is 4 minus 6 plus 5, that is 9 minus 6 is 3 plus x minus 2, f x as p naught is 1. So, it is into 1 plus y minus 1 into minus 6. So, it is x minus 6y, it is plus 6 plus 3 plus 9, 9 minus 2 is 7. So, it is 7. So, this will be the linear approximation of this f. Now, how can you find the maximum error? So, for error term, we first find f x x. What is f x x? F x x from here is 2, f y y is minus 3 and f y y is 0, sorry, and f x y is minus 3. So, m, which is the maximum of over R of mod of f x x, mod of f y y and mod of f x y over the region R, which is given by mod x minus 2 less than equals to 0.1 and mod y minus 1 less than equals to 0.1. Okay. Here these values are constant, they are not dependent on x or y. So, their maximum value will remain the same on any region R. Okay. So, this is 2, this is 0 and this mod is 3. So, maximum will be 3. Okay. And the bound of the error will be given by m by factorial 2, as we have discussed, x minus x naught mod whole x mod x minus x naught plus mod y minus y naught whole square. This m is 3. So, it is 3 by 2. Now, mod of x minus x naught is less than equals to 0.1 as given in the problem and mod of y minus 1 is less than equals to 0.1, both are 0.1, x naught is 2 and y naught is 1. So, this will be less than equals to 0.1 plus 0.1 whole square. So, this is 3 by 2 into 0.2 square, that is 0.04. So, this will be simply 0.06. So, the bound of the error is 0.06. So, similarly we can solve second problem also. Okay. Now, for second problem, how can you find out m? So, let us discuss this. Now, here f x y is e raised to power x cos y, point is 0 0 and the region R is mod x less than equals to 0.1 and mod y less than equals to 0.1. Okay. Now, what is f x? F x is e raised to power x cos y. What is f y? Minus e raised to power x sin y. fx as p naught is simply 1 and fy at p naught is simply 0. So, linearization will be given by, I mean linear approximation of this f will be given by f 0 0 plus x minus 0 fx at p naught plus y minus 0 fy at p naught. This is the linear approximation of this f at p naught. Okay. So, this is f 0 0 is 1 x and fx is 1 at p naught and this is y into 0. So, this is x plus 1. So, the linear approximation of this f is x plus 1. Now, what is the maximum error? How can you find that? So, first we find fxx. Fxx is e raised to power x cos y, fxy is minus e raised to power x sin y and fyy is minus e raised to power x cos y. Now, in this region you see the maximum value of mod of cos or mod of sin is always 1 and the max and in this region it will attain maximum when x is 0.1. Okay. So, we can say that m, which is maximum of over R of mod xx mod yy mod it is mod xx mod xy and mod yy, this will be e raised to power 0.1. Okay, because the maximum value of sin or cos is always 1 and maximum value of e raised to power x in this region is e raised to power 0.1. So, the maximum value will be e raised to power 0.1. Okay. So, what will be the bound? Bound of the error will be less than equals to m by factorial 2 mod x minus x naught plus mod y minus y naught whole square. So, we can solve this and find out the maximum error. Now, similarly, we can do linearization of 3 variable functions. For 3 variable functions, we will be having f p naught plus fx p naught x minus x naught plus fy p naught y minus y naught and this term will be there which is fz p naught z minus z naught. And similarly, the linear approximation, I mean the error bound of this linear approximation is given by m by factorial 2 mod x minus x naught plus mod y minus y naught plus mod z minus z naught whole square, where m is the maximum of all second order partial derivatives, all combinations, and r is given by this region. Say we want to solve this problem, okay, of 3 variable function. So, what is fx y z? It is x square plus xy plus yz plus z square by 4, okay, and p naught is 1 1 2. First we find the linear approximation of this f. So, what is fx is 2x plus y, okay. What is fy is x plus z and what is fz is y plus z by 2, okay. Now, linear approximation of this f will be f at p naught. F at p naught, this is 1, I mean this is x naught, y naught, z naught, okay. This is 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 1 is 5 plus, then it is x minus x naught, that is x minus 1 into fx at p naught. So, fx at p naught is 2 plus 1, that is 3 plus y minus y naught and fy at p naught, this is 1 plus 2, that is 3 plus z minus z naught into fz as this, which is 2. So, you can solve this, which will be the linear approximation of this f at 1 1 2. Now, suppose you want to find out an upper bound for the magnitude of error in the approximation over this region. So, here region is mod x minus 1 less than equals to 0.01, okay, mod y minus 1 less than equals to 0.01 and mod z minus 2 less than equals to 0.02. So, now you find f x x. F x x is clearly 2, f x y is 1, f y z is 1, f z z is 1 by 2 and all other second order partial derivatives are 0, like f y y is 0, okay, like f x z is 0, okay, f x z is 0. So, what is the maximum of all these is 2. So, m will be 2 because it is free from x, y and z. So, it is constant. So, over this region or over any other region the maximum value will remain the same. Maximum of mod of this, mod of this, mod of this and mod of all these, that is 2. So, what is the bound of the error? Bound of the error will be less than equals to m by factorial 2 mod x minus x naught mod x minus 1 plus mod y minus 1 plus mod z minus 2 whole square, and this is less than equals to 1 into 2 cancels out. This is mod x minus 1 is less than equals to 0.01, this is less than equals to 0.01 and this is less than equals to 0.02. So, it is 0.01 plus 0.02, 0.01 plus 0.02 whole square. So, it is 1 plus 1, 2 plus 1 plus 1, that is 4 and 4 square is 0.04 whole square, that is 16, and so that will be the error of approximation. Now, for quadratic approximation, as we already did, so let us discuss this. So, f x y is given as f x naught y naught plus x minus x naught f x at p naught plus y minus y naught f y at p naught plus 1 by factorial 2 x minus x naught whole square f x x at p naught plus 2x minus x naught y minus y naught f x y at p naught plus y minus y naught whole square f y y at p naught plus error term. So, this you can replace by 2 error term. So, this entire term is the quadratic approximation of this f, and this will be the error term or the remainder term. So, how can we find error term here? We can find the quadratic approximation of any f using this polynomial. You find the values of f x, f y, f x x, f x y, f y y at p naught, substitute it over here. So, you will get quadratic approximation of a function f. Okay. Now, for the bound of the error, now here R 2 will be given by 1 by factorial 3 h del by del x plus k del by del y whole cube and f at p dash, where p dash is simply x naught plus theta h and y naught plus theta k, where theta between 0 and 1. So, how can you find the error term? So, let us discuss this. So, first you expand this term and then you replace h by x minus x naught and y and k by y minus y naught. Okay. So, how we will do that? Let us see. First, you will find h del by del x plus k del by del y whole cube, what it is at f of f. So, it is h del by del x plus k del by del y whole bracket into h del by del x plus k del by del y whole square f. So, we have already seen that this term is h square f x x plus 2 h k f x y plus k square f y y. So, this we have already seen. Okay. When you operate this operator on this function, so what you will obtain now? This is h square f x x plus 2 h k f x x y plus k square f x y y plus, so this term is here over here, plus k times h square f x x y plus 2 h k f x y y plus k square f y y y, and this will be h cube f x x x plus, it is 2 h square k and also h square k, we are taking both are same. So, 2 h square k f x x y plus, so it is 3, yeah, okay, 2, it is 3, 2 times here and 1 times here, so it is 3, and similarly here 2 h k square f x y y plus k cube f y y y. So, this is the term, this is this term, and now you replace h by x minus x naught and y by and k by y minus y naught. So, what you will obtain? So, what is R2 mod of R2? So, first find R2 and then we will find mod. It is 1 by factorial 3, it will be x minus x naught whole cube f x x x at p dash, okay, plus y minus y naught whole cube f y y y at p dash plus 3 x minus x naught whole square y minus y naught f x x y at p dash plus 3 x minus x naught y minus y naught whole square f x y y at p dash, where p dash is simply x naught plus theta x minus x naught and y naught plus theta y minus y naught and theta between 0 to 1. Okay. So, simply replace h by x minus x naught and k by y minus y naught, you will get this expression. Now, suppose you have a region R which is x minus x naught less than equals to say h1, y minus y naught less than equals to say h2, and in this region let us suppose the maximum of mod f x x x, mod f y y y and mod f x x y and mod f x y y, this maximum is say m. Okay. So, we can say that R2 this modulus will be less than equals to, now this is maximum is m. So, this will be less than equals to m, mod of this less than equals to m, less than equals to m, less than equals to m. So, m will be common, m can be take out, and inside the bracket you will be having mod of this cube, I mean this will be mod x minus x naught whole cube plus mod y minus y naught whole cube plus 3 mod x minus x naught whole square y minus y naught plus 3 mod x minus x naught into mod y minus y naught whole square, and this is nothing but mod x minus x naught plus mod y minus y naught whole cube. So, in this way we can find out the error bound of the error for quadratic approximation. So, we can discuss this example is very simple, let us discuss this. So, similarly we can think for higher approximations, cubic approximation or approximation of degree 4 using the same concept. Okay. Here I have discussed linear approximation and quadratic approximation and the corresponding error approximation, okay, or the error bound. Now, function is sin x sin y. Point is 0 0. Now, when you find f x, it is cos x sin y. When you find f y, it is sin x cos y. When you find f x x, it is minus sin x sin y. F x y, it is cos x cos y. F y y, it is minus sin x sin y. Okay, because we want quadratic approximation. Now, when these values at 0 comma 0, this is 0 because of sin 0, this is 0, this is 0, this is 1 and this is 0. So, we are leaving with only one value at p naught, which is f x y. Now, what is the quadratic approximation of any f? Quadratic approximation of f will be given by f at p naught plus x minus x naught f at p naught plus f x at p naught y minus y naught f y at p naught plus 1 by factorial 2 x minus x naught whole square f x x at p naught plus 2 x minus x naught y minus y naught f x y at p naught plus y minus y naught whole square f y y at p naught. Now, this is 0, this is 0, this is 0, this is 0 and f at p naught is also 0. So, we left with only this term which is 1 and x naught and y naught are 0. So, this is 2 by 2 which is 1. So, this is given by x into y. So, x into y is the quadratic approximation of this f. Now, to find the bound, now what is the bound? So, error bound is given by m by factorial 3 mod x minus 0 plus mod y minus 0 whole cube. Now, to find m, which is the maximum of mod f x x x all third order partial derivatives, all combinations. Okay. So, maximum over this region when mod x is less than equals to 0.1 and mod y is less than equals to 0.1. How can you find that? Now, any combination of like f x x x or f x y y will contain the terms of sin and cos only, and the maximum value of sin into cos is always 1, because the maximum value of sin is 1 and cos is 1. So, we can simply say that upper bound of m will be 1. So, we can say that R2 mod of R2 will be less than equals to 1 by 6 and this is 0.1 plus 0.1 whole cube. So, we can simplify this and this will give error approximation of this quadratic approximation over this region R. Okay. So, that is all about this lecture. So, thank you very much.